those things we have seen. Uh, so today what we'll do is we will see in this electromagnetic theory paper, that is course 2. We will see the what we call electromagnetic wave propagation at the interface. Okay, electromagnetic wave propagation at the interface we'll see here today. So actually, as we have discussed in the last classes, like the electromagnetic waves, how it will be traveling when it is moving in what we call in any like a free space or in a homogeneous medium or in any dielectric medium. So in that, what will happen means you'll be having particularly one type of medium you are going to be have. Then its propagation will be like what we call it will be same as it will be moving in the same material medium. Like suppose if I take any free space in which the charges are not present, the electromagnetic wave will be moving in free space. It will be propagating its on its own properties. Suppose if it is moving in an dielectric medium, it will be moving with same means some other with the different propagation. It is going to be there. Now we are going to be study about here. It is when the electromagnetic wave is moving from one medium to another medium. So what is that we'll see here. Just I'll share the notes and then I'll discuss. 1 minute. So here what I'm sharing is okay. So here, as we know that this chapter which we have is this part. We are seeing this electromagnetic waves at the interface. 1 minute. Right. So this part, the electromagnetic waves. 1 minute. So at the interface, okay, this is what we are seeing, how the electromagnetic wave will be propagating at the interface. So actually, as I told that when we have studied about the electromagnetic wave which is propagating in different media, it is different media means whatever may be the media we have, like a free space or a dielectric media or some other thing, it is having its what we call propagating. When it is propagating in a free space, it's having its propagation in different manner. When it is propagating in dielectric medium, it is going to be having different manner. But whereas when it is propagating at the interface is nothing but, suppose actually what I'll say is we will be having, like suppose this is the interface which is having. Okay, so why I'm calling it as interfaces means the above of this whichever we have, this is one media we have, and below here we will be having different media. Say that this is the medium 1 which we have. Okay, this is the medium 1 if you have, and the below one which we have is the medium 2 if you are having. Understand? This is the medium 2. So in between this, the place which is separating these two media, we will be calling it as what? Interface. The place which is separating these two media will be calling it the interface we are going to be calling. So these media, one, medium two, if you take any examples like this, maybe medium one may be having the air medium, or medium two may be having the glass medium, or air medium, or water medium. Like this, we have different examples for this, what we call different medias we have. So here what we are seeing is when this electromagnetic wave, when it is propagating from one medium to another media, how it is going to be means of propagating, what are the propagating properties it is having when it is moving from one place to another, one medium to another medium. That is what we have to see here in this one. Okay, so when it is moving, so we are going to be get different things we are going to be get into consideration, like actually you'll be having what we call the electromagnetic wave which is incidenting in medium 1. Say that if it is coming in this medium, in this manner, if it is coming, so if it is interface, it is interacting the interface with certain angle here, that we are going to be call it as a angle of incidence. Suppose if I draw here, so here in this manner, is going to be hitting the interface. This maybe we'll be calling it as a what we call incident angle theta I we can represent here. So as we know that whenever a wave is what we call interacting with certain interface, that means which is separating the two media, after hitting this interface, what will happen means some part may be reflected back, which we will be calling it as what reflected wave we are going to be called, and generally this will be theta r we are going to be have. So generally we know that by the law of reflection or which laws whichever we have, the incident angle should be equals to the reflecting angle you should have. Theta I is equals to theta r you should have. And at the same time, whenever after reflecting, some part of this incident wave may be what we call transmitted or refracted we are going to be called. So this is what we call it as a refracted wave. So this is the incident wave and this is a reflected wave we have, and this wave which is moving into the second medium, which we'll be calling it as a refracted wave we are going to be called. Okay, we'll be calling it as a refracted wave, sorry. So this is nothing but the transmission is going to be occur. In some cases, what will happen means the absorption of the electromagnetic wave is also going to be takes place here. So like this is when the what we call a electromagnetic wave is is incidenting at the interface. You are going to be have what we call incident wave will be there, reflected wave will be there, as well as the refraction wave will be there. So we will write what are the equations for this incident wave, what is the equation for reflected wave, and what is the wave what we call a refracted wave equation we are going to be write, and we can see the general solution and all those things. So first in this, as we are studying here, in this we are going to be study about first the boundary conditions whenever this what we call a electromagnetic wave is interfacing at two different media. And generally here what are the different things which we are going to be come across here? It is we will be having like a medium one is there and as well as the medium two is there. So in the medium one we will be having different electrical properties, and as well as the in the medium 2 also you are going to be have the different electrical properties. Understand? So if I take the permittivity of the medium, generally we'll write it as epsilon 1 in this one. Epsilon 1 will be the permittivity of the medium 1 you are going to be have. And the permeability will be like a mu 1 we are going to be taken. And the conductivity you are going to be write it as a sigma 1 or we are going to be write. So generally we are dealing with this epsilon 1 and as well as the mu 1. And coming to this medium 2, this may be having different electrical properties as it is different medium. So as we have taken some example of air or glass medium, we have taken air glass medium. So the medium 2, it is going to be have the permittivity of epsilon 2 you are going to be have, and similarly the permeability you are going to be have is mu 2 you are going to be have. Okay, these are the things you should remember when we are studying about this one. So now we'll see the boundary conditions here. Okay, boundary conditions we are going to be see. Then the different boundary conditions we are going to be see like for a boundary condition for what we call electric displacement vector we are going to be see, and as well as the boundary condition for magnetic induction, and boundary condition for this what we call electric vector, as well as the boundary condition for magnetic vector. So because these four boundary conditions whichever we have, we can expect one of the boundary condition in your examination as a short question. That is what important. These boundary conditions are very important. You can expect this as a short question. Any one of the boundary condition they might be asked to derive that may be getting in your examination. Okay. So now here we'll see about this boundary condition. 1 minute. So here, just like we'll see here, what are the four boundary conditions we have is like a boundary condition for like a E, B, D. You are going to be have. So this is one of the parallel component we are going to be called, that is E1 parallel is equals to E2 parallel, and as well as D1 normal is equals to D2 normal, and as well as the one is a B1 normal is equals to B2 normal. Generally, we'll call it as a perpendicular also instead of normal. So we will see the boundary condition by using the we call this Maxwell's equation. Okay. So here we will see about first boundary condition. So that is the boundary condition for electric displacement vector. Okay. So boundary condition for electric displacement vector we are going to be see. So in order to derive this boundary condition for electric displacement vector, we will be using the Maxwell's equation. That is the first Maxwell's equation. Del dot D is equals to rho. Actually, it is not P. Del dot D is equals to rho. Actually, it is written as a P, but you make correction in your books you may be having. So it should be del dot D is equals to rho. Okay, this is the first boundary condition. As we have seen the four Maxwell's equations, first two Maxwell's equations, they are dot product you are going to be have, and next two Maxwell's equations will be cross product which we have. So by using this Maxwell's first equation, we are going to be derive the boundary condition for this what we call electric displacement vector. So in order to derive this boundary condition for electric displacement vector, what we are going to be consider is we are going to be consider here 1 minute. We are going to be consider here a small pillbox we are going to be consider. So why the pillbox and all those things I'll explain here. So generally here what we have is we are going to be take some surface we are going to be taken. So this is the surface which we are having. So in this surface, if I say that the above part it is a medium one we have, okay, and below part which we have is medium two you are going to be taken. So in order to get the boundary condition, what we are going to be take is we are going to be consider a surface which is covering the two different media. Like this is a surface, small surface means small pillbox we are going to be taken. So we will apply this what we call a Maxwell's equation for the small pillbox, and we will be taking these two for entire volume by using some what we call Stokes theorem in some cases. In some cases by using the Gauss theorem. Why? Because the Gauss theorem is nothing but which will be converting the surface integral into the volume integral, and as well as the Stokes theorem which will be converting the surface integral into the line integral. So we will make use of these two laws like a Gauss divergence theorem or Stokes theorem whenever we require, like when we are converting this surface integral into volume integral or volume integral into surface integral, we will be make use of this Gauss divergence theorem. Then we will be using Stokes theorem when we are converting the surface integral into the line integral here. So first, this is the entire surface which we have. So in this surface, we'll be having the medium one and medium two, both mediums we have. So in this, what we are taking is we are taking a smaller portion of this surface, like this pillbox. So this is what actually we are going to be consider. That means it is going to be cover the medium one as well as the medium two. So this small pillbox, this can be drawn in this manner. Okay, this can be drawn in this manner. So the pillbox actually. So means you'll be having the above surface, below surface, and it is having some height. Actually, the surface whichever we are going to be have, this is having certain height. So here, this is what we are going to be drawn here. So this is a surface S1 whichever we have, and this is the surface S3. This will be of S1 and S3 will be of one medium, and S2 and S4 will be of another medium you are going to be have. As I told that we are going to be have like medium one is having the permittivity of the epsilon one, and the medium two is having the permittivity of the epsilon 2, and as well as here it is not written, but mu1 will be the permeability in this medium and mu2 will be the permeability of this medium. So this pillbox whichever we have been taken, it is going to be get four different surfaces you are going to be get. S1 is completely in the medium one you have, S2 is completely in the medium 2, and S3 surface whichever we have, the S3 surface one side will be in the medium one, and another surface in the medium two we have taken it as a S4 we have taken. So this is what how the interface we are going to be have, and this H is nothing but the height of this surface interface whichever we have been taken. This small part whichever we have, no, this we have taken this much height we have taken. Generally, this height, whichever we have, which is separating the medium 1 and medium 2, is having very infinitesimally small area it is going to be have. Otherwise, we can say that it is going to be have infinitesimally small height, which we are going to be have. So now we have been taken this pillbox and we have drawn here. 1 minute. We have taken the small pillbox and this is what we have drawn. Okay. So 1 minute. Right. So here, this is what the pillbox which we have taken, and these are the different surfaces we have discussed. And what we have considered here it is we have considered the Maxwell's equation del dot D is equals to rho we have taken. And as we have taken the pillbox which is in a cylindrical shape, so we call it as a cylindrical pillbox we are calling. And the surfaces are S1, S2, S3, S4. S1 and S2 are actually the surfaces which are in medium 1 and medium 2 completely. S3 and S4 will be one above the medium of means it will be covering the medium 1 and S4 will be covering the medium 2. That is what we have. Now, what we have taken is the Maxwell's equation, whichever we have taken, del dot D is equals to rho. You make correction in your book so that it is not P, actually it is a rho. Okay, now what we are doing is we are integrating this over the pillbox. Okay, that means we are integrating. Why we will integrate means in order to get the entire volume, we will be integrating. Otherwise, simply instead of saying that integrating over the pillbox, simply we can say that the Maxwell's equation, whichever we have taken, that we are integrating over a volume. So that is the reason why here we have written this divergent of dV we have written. Okay. So the same Maxwell's equation, whichever we have, we are integrating. So over a volume, we are integrating on both LHS and RHS. So see here, we have like a row here. Previously, it is not row, it is a V, it has been written. It is not V, it is not P, it is a row. You have to be changed. Right. Now, after integrating over the volume, now what we have to do is we have to convert this part, the LHS part, whichever we have to be convert this into the surface integral. What we have to do? We have to convert this into the surface integral. So in order to convert this volume integral into the surface integral, we will be taking the Gauss divergence theorem. Okay, we will be taking the Gauss divergence theorem. So this by using this Gauss divergence theorem, we can convert this volume integral into the surface integral. So you see, after applying the Gauss divergence theorem, this has been converted into the surface integral here. Okay, this is the surface integral. That is surface integral of d dot ds instead of surface volume integral of divergent dv. We have got the surface integral of d dot ds. So mainly we will use the Gauss divergence theorem in order to convert the volume integral into the surface integral, right? So now what we are doing is we will be applying this one for entire pillbox. We are going to be the entire pillbox means the surface which we are taking here. So there are four surfaces which we have. So for the four surfaces, the same surface integral we are applying here. So in order to apply this, so we have taken the first one, that is the surface integral of S1 D1 N1 dot ds. Sorry, D1 dot N1 ds. So this N1, N2, N1 or N1 dash, whichever we are used, these are nothing but the unit normals. These are nothing but the unit vector normals, which we are calling. So at the surface one, it is surface integral of S1 D1 dot N1 cap. And similarly, a surface 2, that which is present entirely in the medium 2. So this is what we have, because D2 is the displacement vector in this one. And similarly, this S3, S4, whichever we have. So this is what we have written. So this one is a D1 dash dot N1 dash, and similarly, this is D2 dash and N2 dash. Why we have written D1 dash, D2 dash is nothing, but this is actually the interface which is converting from one medium to another one. So here we have written, you see, so we have written clearly here where D1, D2 represents the electric displacement vectors in the medium 1 and medium 2, and this N1 and N2 represents the unit normals in the corresponding mediums, like in 1 and 2 medium. And as I told that the height of the pillbox is very small, means which we is a very infinitesimally small, as I told that. So that means its value is going to be tending towards zero. its value is going to be tending towards 0. So as it is tending towards 0, you see we have written this limit here, the limit which we have written here, right? So this limit h is tending towards 0. That is nothing but the height of the pillbox, whichever we have. Actually, it is like this. It is like this. So actually, this is the surface which we have. So in this is the height of the pillbox. If you observe this one as compared to the surface, the h value is 0. But actually, we have represented like this much of height we have represented. But in order to understand this much of height, we have to be taken. But actually, the h value is very small. So h value is tending towards 0. So what we do is here is we are going to be neglect the third and fourth terms whichever we have. We are neglecting means its value is almost equals to 0. So that is the reason why we are going to be neglect. So this is the third and fourth terms. This S3, S4, these two terms we are going to be neglected. So that as the limit value h is tending towards 0, the four this term and as well as this also, that is the surface integral of v rho dv. So this value, that is on LHS, these two terms, okay. So these two terms is going to be getting equals to 0, and as well as in the RHS, this value is also going to be getting equals to 0. So that is what we have written here. As limit is tending towards 0, this value is present and this value is going to be present here. Okay. So here, a minute, right. So here, this value is tending towards 0. This value remains here, and this two S4 value will be 0. So as we have taken this value we have here, that is surface integral of S1 D1 dot N1 dash and the surface integral of S2 D2 dot D2 dot N2 dot ds, and this RHS you are going to be have. After doing this surface integral, this value will becomes d1 dot n1, and this is going to be area. This integration of ds you are going to be get it as the area. The area will be same both in the medium 1 and as a medium 2. You are going to be have the same medium area. So this one is same. Now after this, what we'll do is we will be dividing with a on both sides. Okay. So we'll be dividing with both sides with a, so that a will be get cancels on both sides. Uh, so here, right. So we'll be dividing on both sides with a, and so a value is going to be get cancels. And one thing you have to remember, it is n2 value and n1 value. N1 value will be n and n2 value will be minus n. Why it is minus n means in the pillbox we have taken this is a pillbox. So this will be in this direction you are going to be have, which is a normal one, and another will be in this direction. So n2 will be in this direction. But whereas n1 normal vector and n2 normal vector both are same, but only the thing is opposite in direction. So that is the reason why this minus sign we are getting at this point. Okay, so we are getting the minus sign at this point. So after that, so on the RHS, which we have done the integration and we have got it as a sigma a, where sigma is nothing but it is a conductivity. Okay, conductivity which we have. So we have got d1 dot n minus d2 dot n is equal to sigma. So this we are writing it as a d1 n minus d2 n is equal to sigma we are writing here. So this is what actually the boundary condition for electric displacement vector. Okay, electric displacement vector. So with this, we can say that this d1n, or otherwise the electric displacement vector, is not continuous. If it is continuous, d1n should be equals to d2n, it should be half. But it is not equals, d1n is equals to not equals to d2n. So it's d1n minus d2n is equal to some sigma value we are getting, that is the conductivity. So it is not continuous. That is what it has been written here at this point. Okay. So it is not continuous. 1 minute. It is not continuous. That is what it has been written at this point. Let's see. This one. It is not continuous. Electric displacement vector is not continuous at the interface. Okay, but it changes amount equal to how much? the surface charge density, sigma is surface charge density here we have been taken. So that is what we have. So d1n minus d2n. In some books, the notation will be in different manner. You are going to be have like a d2n minus d1n should be equals to some rho s they are going to be given. So no problem. Same thing it represents. So d1n minus d2n is equal to sigma, or d2n minus d1n is equal to rho s, whatever it may be. All these are same only. The representation is different. That's all. So don't get confused. In some books, they'll be writing in different manner. So here we are. This is the boundary condition for the electric displacement vector. Now we'll see the boundary condition for this magnetic induction, right? So next we'll see the boundary condition for this magnetic induction. That is, magnetic induction is represented with B here. So in order to get this magnetic induction boundary condition, again we have to take one Maxwell's equation, as previously we have been used. First Maxwell's equation we have been used, and this is the second Maxwell's equation which we have, that is del dot B is equals to rho. Okay, this Maxwell's equation we are using. Understand? Del dot B is equals to 0. All in order to get all these four boundary conditions, we have to use four Maxwell's equation in different cases. So this is what we have. Again, what we did is we have taken the volume integral. Okay, understand? We have taken the volume integral. So as we have taken the volume integral, so that is integration V del dot B dV is equals to 0. And what we'll do is same thing again. We are going to be converting this. What we call volume integral into surface integral by using this what we call Gauss divergence theorem. We are converting this volume integral into the surface integral. So we have got here surface integral of b dot ds we have got. So now again, by taking the pillbox, we are going to apply for the four surfaces as we have applied previously. We are applying here, and again by taking h value of height of the pillbox is very small, that is infinitesimally small, it is going to be tending towards 0. So the three terms, that is third term and fourth term, this is going to be 0, and RHS anyhow it is going to be 0 we have. And by applying this surface integral, this n1 dot ds, whichever we have, the surface integral of ds, you are going to get it as area, so that we are getting b1 n1 a plus b2 n2 a is equals to 0 we are getting here, right? So now, as we know that both n1 and n2 are in the opposite direction, so we are going to be taking it as one of them as negative. We are going to be taken, so it will be b1n minus b2n is equals to 0 here. Or this b1n minus b2n, we can write it as a b1n minus b2n. Otherwise, b1n is equal to b2n we can write. So this is actually equation 4. Don't get confused that this is equation 4. Actually, it should be like this, but they have written in this manner. This is equation 4. So the condition is b1n minus b2n. It should be equals to 0, or we can write this as b1n is equals to b2n we can write. In some books, the notation will be the tangential component of this B magnetic induction is also equal. They'll write this B1T is equals to B2T, they'll write. So this is tangential component or normal component, all here are going to be same. So don't get confused that, and this will be same. Here we have represented in the form of a normal. So we have written this as B1n minus B2n is equals to 0 we have been written here. Understand? So this is what the boundary condition for what we call this magnetic induction B. Okay, so this is we have, and then we have like a what we call as we have represented like in the previous one, that is the electric displacement vector boundary condition is not continuous, because there we have got a d1n minus d2n is equal to some sigma value we have got, but here we have got b1n is equal to b2n. We can say that this is continuous across the interface. Okay, this is the normal component of the magnetic induction. B is continuous across the interface. This is the boundary condition. So you can represent in the form of what we call like a mu1 h1 perpendicular is equals to mu2 h2 perpendicular, because we can write a B in form of h, so we can write this also, right? So next we'll move to the another boundary condition, that is the boundary condition for electric intensity vector here. Okay, we are going to see next boundary condition for electric intensity vector we have to see. Right. So here, in order to get the boundary condition for electric intensity vector, as we have taken the example of the pillbox, that is a smaller area we have been taken. So now here what we are doing is we are considering a rectangular loop we are considering, which is ABCD. Okay, this is the ABCD loop. Again, here if you see, this is the interface we have. Okay, interface at this point, which will be having above the interface we have the medium 1 we have, and the below the interface we have the medium 2. And in the medium ones, the same electric intensity vector we have been taken it as a E1 we have been taken, and whereas in the medium 2, the electric field intensity vector we have taken it as a E2 we have been taken. Okay, so this is the rectangular loop, which is a closed loop we have. So this is A, B, C, D. This is what we have, rectangular loop. So in this, you have to note that, so the value of AB is equals to the, what we call the value of CD. That means the length of AB and CD both are same we have here in this case. Okay, AB and CD are same. So generally, as we have got a four surfaces in the previously, in this case also the length AB we are going to get length BC, width BC, CD length, and as well as the AD width we are going to get here. So now, in order to prove this boundary condition for electric field intensity vector, we are going to be taken the Maxwell's third equation we are going to consider. Understand? So here you should note down that length of this will be L and height of this will be H. You have. So third Maxwell's equation we have been taken, that is del cross E is equals to minus dou B by dou T we have been taken. Now, what we have to do is we have to apply this surface integral to this one. That is a surface integral of del cross E n dot ds, and as minus on the RHS we have surface integral of dou B by dou T n dot ds, where n is nothing but the unit vector which we have. Right. Now, as in the two previous cases of the boundary condition, we have been taken the Gauss divergence theorem to convert the volume integral into the surface integral. But whereas in this case, in order to convert the surface integral into the line integral, we are going to be use the Stokes theorem. So you see, what we are using is here we are using the Stokes theorem we are using. So the Stokes theorem already you might be studied in the graduation level. We have like a which will be converting the surface integral into the line integral. 1 minute. So here we are using the Stokes theorem, which we are converting the what we call the surface integral into the line integral. We are converting by using the Stokes theorem here. So by using this Stokes theorem, we will convert now this surface integral into the volume integral. So when we are converting the surface integral into the volume integral, you see del cross E dot n ds, we can be getting it as a line integral A B C D E dot dl. Why I'm writing here directly A B C D E dot dl is because the entire what we call a rectangle we have to be taken. We are writing this as a surface line integral of A B C D. We are writing here. Now this line integral of A B C D which we have, we will be converting into the AB length as well as a BC length as well as again a CD and as well as a DA. So here in this case, if you observe here, here we have like a, you see, we have written this part into this all we have written. Right. So in the medium one, length as AB we have written, and E1.dl we have written, and as well as the medium 2 we have been written, this is a E2.dl CD we have written. And the third integral which we have written here, it is by combining this BC and AD we have been written. Okay, this one we have been written by combining the BC and AD. Why we have been written by combining BC and AD? This is in both the mediums you have. You see this BC and AD. BC is present in the medium 1, medium 2, and AD also present in the medium 1, medium 2. Whereas AB and CD present separately in the medium 1 and medium 2, whereas this BC and AD present in both the mediums. So we have been written this combining these two we have written here. Okay, by combining these two we have been written here. 1 minute. Right. So this part which we have here, this right. So this one we have written combining these two. Right. Now again, by taking the height of this rectangular loop into consideration, so we have like a ABCD and BCAD. So the height is tending towards 0 as it is infinitesimally small. Here this value which we have third term in this equation 3 is going to be get equals to 0. That is the reason why here this value we have written as equals to 0 we have written, right? So next, similarly on the RHS, the term which we have is that is integration surface integral of dou b by dou t. This value is also going to be 0. This value is also going to be 0. Why it is going to be 0 means the B is actually the magnetic induction whichever we have. The rate of change of B value is equal to 0 because the B value is constant throughout the surface. That means it does not changes. The B value is constant throughout the surface. It does not changes. So the rate of change of constant will be equals to 0. So therefore, the value of dou B by dou T is going to be getting as equals to 0. This value is going to be getting equals to 0. Here you are going to be get, right? So as we have taken both these equals to 0, we have taken, right? So these values, this value and this value is equals to 0. The remaining will be only this we have, okay, this value. So now we convert this integration into normal. That means we will be doing the integration, right? Because the other two terms are zeros. So we have like E1AB plus E2CD is equal to 0. One thing we have. And as we know that AB and CD both are in opposite direction, again, we will be taking into the negative sign here. So we are getting it as a E1AB minus E2AB is equal to 0. Otherwise, we can write this as a E1 perpendicular L minus E2 perpendicular L because AB value is L. So we have written E1 perpendicular minus E2 perpendicular L is equal to 0. And we can write this as also E1T is equal to E2T. That is, the tangential component of the electric field vector is equal in both the media or it is continuous, we can say here. So you see, we'll write here. This is what we have, right? So here also we have written here, you see. So where E1, E2 are tangential component of the electric field in the two media, and we have written that E must be continuous across the interface. That means whenever the electromagnetic wave is traveling from one medium to another medium, its E value is continuous. It does not changes. In both the same cases, it is going to be have the same value. That is what we have. This is the boundary condition we have. And you should remember here that among these four boundary conditions, you will get one in the examination as a short question. Otherwise, they may be asking to derive the four boundary conditions as a long question. So you have to go through these thoroughly, four boundary conditions, so that you'll be getting one question compulsory in your examination. You make it a note of this, okay? As you are make it this question as an important question in your books. 1 minute, I'll be. Right. Next, we are going to be see about the boundary condition for H. So same procedure as we have followed previously, but only the thing is we are going to take the fourth Maxwell's equation, that is del cross H is equals to J plus dou D by dou T we are going to be taken. Next, what we did, we applied the surface integral on both sides. And again, we will be converting this surface integral into the line integral by using the Stokes theorem. So we have got this line integral of ABCD H dot DL. And the RHS, we have the same S. We are not converting on the RHS, only LHS we are converting. And again, this we are writing in detail here for AB, for CD, and combining BC and AD because this is present in both the media. And again, as we know that this value is going to be 0 and this value is going to be 0. So, sorry, in this only the value of this entire value will be 0. And here, in the surface integral, we can write surface integral of J dot n cap ds. We are separating simply plus surface integral of dou d by dou t and ds we are going to be. This part is going to be 0 because d is constant throughout the surface. The rate of change of d will be 0. This value is equal to 0, whereas this value is not equal to 0. This value we are going to get it as a j here. Surface integral of j we are going to get it as a js perpendicular we are going to get. That is what you have to remember. The entire value of this RHS is not equal to 0, but only the dou d by dou t part is going to be 0 and the j part will be here. We have written 1 minute. I will show. So this value, surface integral of j dot and you are going to get. So this is what we have. So I'm rounding off here. See. This one. Okay. So, and we know that if you do the integration, we will be getting it as a this one H1TL minus H2TL. And we know that both are in opposite direction. We are getting the negative sign here. And on the RHS, we are getting the JS perpendicular L. So if we remove this L, we are getting H1T minus H2T is equal to JS perpendicular we are getting. Here, if you see, this tangential component is not continuous. It is not continuous. As we have studied about the four boundary conditions we have studied, among the four conditions, two are continuous, whereas two are not continuous. That you have to remember. Okay. So this is four Maxwell, four boundary conditions. And then we will move to another part that is, as I told, that reflection, refraction, and as well as the reflection, refraction you are going to be have. Now we are going to be study about the reflection and refraction at the dielectric interface. We are going to be study about the dielectric interface. We are going to be study this. So in order to study this, we have been considered here medium 1 on the LHS and medium 2 on the RHS. So this entire part will be medium 1 and medium 2. So in this case, on the left hand side of this one I'll show you 1 minute. So here, how it has been divided, I'm showing here. So this part, right? So this is what we are separating the medium. This entire part is in medium 1, and this entire part is medium 2. This is how it is separating. Okay. So in the medium 1, as I told, that electromagnetic wave is going to be incident and it will be reflected back like this. Suppose if I draw here in this one, so in this direction it is incidenting, some part will be reflecting back, some part will be transmitting, otherwise refraction. So this is incident wave, this is a reflected wave, this is the transmitted wave we can call here. So by taking this into consideration, we are going to be study about the reflection, refraction of the electromagnetic waves at the interface we are going to be study here. Understand? See here, we have been written different equations like EI, BI, VI for incident wave And for the reflected wave, ER, VR, BR. And this is for a transmitted wave, ET, BT, and VT. Along three directions we have to take. Here, this is what the equation of the incident wave, which we have represented with equation 1. And here we have been converted like the values of H by using this. Already we have discussed this B value and H value in the previous unit. You can go through those. We can write H is equal to this in the form of 1 by mu omega K cross C. B is equal to this. We can write just the mathematical equations are there. Just you can solve this. It is easily can know. So we have written EI is equal to this one. That is the E naught I exponential of I K I K R minus omega T, because it is an incident wave. We have written Ki. So generally K will be there. Okay. So I is nothing but the subscript, whichever it is denoting the incident wave. Okay. So B we can write in this manner. And similarly, for reflected wave, we can write this ER is equal to E exponential of this value, and BR is equal to this value. We are going to be right. And for the transmitted wave, we can write E value and B value with this. Okay. So as we have like E naught I, EORI, EOT, these represent the complex variables of the incident, reflected, and as well as the transmitted waves. Okay. Now we'll see the reflection and transmission coefficients. So far, whatever we have studied here, it is simply we have written the equations for the incident wave, reflected wave, as well as the transmitted wave equations we have written. Now we will see the coefficients, that is the reflection and transmission coefficients we see. So we know that always the transmitted wave should be equal to the combination of the incident and reflected wave. So we will write this as usual. So generally this one we have for incident and reflected wave, and incident and reflected wave for B and E we are writing. So it should be combination of both should be equals to transmitted wave. So that is what we are writing. And whereas if you take this what we call Ki value, Ki value is not going to be changes. It will be the same for incident wave, reflected wave, as well as the transmitted wave. It is the wave vector K value will be same for all this. Okay. By taking into consideration that, so here we are writing EI plus ER is equals to ET, HA plus HR is equals to HT we are writing. And corresponding equations we are writing. Simply H we can write it as a B by mu. So we are writing this one. Now these values we are substituting here. And here we have a incident wave and reflected wave. If you see, if you observe here, the incident wave will be positive sign you have, whereas the reflected wave will be negative sign. Why? Because it is traveling in this direction, reflected wave is traveling in the opposite direction. So that is the reason why here we are writing the minus sign. So this minus sign. So all these mathematical derivation, just you go through this one, because we cannot explain each and every term mathematical these things, because you have to solve those. So within the time, in a stipulated time, we cannot do all those things. So you go through the derivations, it is easier, but whatever may be the important points, whichever we have, that I'm explaining here. So minus sign is why we have been taken is because it is reflecting back. Minus sign we have been taken. That is what we have applied, and we are we are getting this as finally in this manner. This we are solving because this is a equation 7, whichever we have got here. It is this one, that is EOI plus UR is equal to EOT, and equation 8 is nothing but in terms of beta we are writing. So if you solve this, so we are going to get this equation. Okay, this is the equation we are going to get, that is EOR is equals to this value into EOI you are going to get. So that is nothing but VT minus VI by VT plus VI into EOI you are going to get. Okay, so if you want to write this in terms of transmitted wave, so EOT should be equals to this value you are going to get. So all mathematical part I'm not explaining, go through those. Okay, so this is what we have. This is the equation which we have, and we will be talking about the special cases here. Special cases means if the electromagnetic wave which is traveling its velocity is greater in the transmitted wave than the incident wave. One case you are going to get, and another case is the velocity of the electromagnetic wave, which is having less velocity in the incident medium. Okay, so these are the three different cases you are going to get. In one case, if Vt is greater than Vi, this is condition you are going to get. This is the condition, that is EOR is equals to EOI you are going to get. Understand? This condition you are going to get in this case. If it is velocity is less than in one medium, another medium, Vt is less than Vi, because incident wave and transmitted both are in different mediums. So that is the case. So this is what you are going to get. And say that if both the mediums are same, otherwise the velocity in the incident medium and transmitted wave is same, then this is the condition you are going to get. EY is equal to going to get. So this is what the reflected and incident waves in different mediums we are going to get here. Equations for them you are going to get different manner. Okay. So now we will see this Fresnel's equation. So don't get confused that Fresnel's equations you are going to get in different cases you are going to get. Here we'll get the Fresnel's equation. In some other topic also you are going to get the Fresnel's equations. So here the Fresnel's equation is for particular in this case. Okay. So generally the Fresnel equation here in order to get, we will have the refractive index is nothing but the ratio of the velocity of light in to the velocity of the medium. Okay, velocity of light to the velocity of the medium, right? So by taking this into consideration, we will get this, as we have got the EOR and all those equations, we'll substitute those, we will get these equations. So final equation which we get is this equation 13(1) we are going to get, that is EOR by EOR is equal to N1 minus N2 by N1 plus N2, and the 14th equation which we are going to get it as a 2N1 by N1 plus N2. These 13 and 14 which we will be calling it as a Fresnel's equation in this corresponding what we call here for this one. Okay, for this one, reflection and refraction of plane electromagnetic wave when it is normal incident, that you have to remember. So Fresnel's equation for the normal incidence. Here we are talking about only the normal incident we are talking. Oblique incidence is other than the 90 degrees, whichever we are going to get. That is what we have. So here we are getting. So here, these are the two equations which we are getting, 13 and 14 are the Fresnel's equation for the normal incident. Okay. Similarly, we can calculate the power reflectance and transmittance. So here, this is what the equation for average energy flow per unit area, which we will be calling it as a Poynting vector. Okay, this is what that is defined by E square by RMS. So we will substitute those values. We will get this equals to 1. So here on the RHS, whichever we have, how we are getting all the values, here it is written. So this is actually equation. In this E square RMS, how we are writing, what is the value we are getting, what is the Z value, what is the V value, all it is given. You can easily understand if you solve, otherwise you can't. So you solve this, so we are getting average value is equals to I we are getting. Understand? So here the incident power density, the reflected power density, and as well as the transmitted power density is given by these equations. Okay, so this is what we have the energy, which is average energy. This is the average energy flow per cycle of the electromagnetic wave. And similarly, energy is conserved in order to show that R plus T is equals to, you'll get it as a 1. R plus T is equals to 1, we are going to get. So in order to show that energy is conserved, R plus T, that is nothing but the amount of reflected plus transmitted should be equals to 1, you are going to get. Already we have done the equations. So if we substitute those, we'll get this is equals to 1. Okay. This is the reflection and reflection of the electromagnetic waves in the normal incidence which we have. Now we'll go for this reflection and refraction of the electromagnetic waves for oblique incidence we have. So this is oblique incidence. Oblique incidence is nothing but other than the 90 degrees, whatever we have, that is what we have. For the oblique incidence also, what we will do is we will write all these equations like a incident wave, a reflected wave, as well as a transmitted wave. For the incident wave, we'll write the equation for all. So this is medium 1, mu1 epsilon 2, medium 2, mu2 epsilon 2. Mu2 epsilon 2 we have, and all these equations we are going to be writing here. So same procedure as we have followed for the normal incident. Same equation for E we are writing, equation for B we are writing. Okay. B are writing, ER, BR we are writing, and similar to ET, PT we are going to write. Here, the mistake is there, equation 5, it should be ET, it is not EI. It has been noted like EI, but actually it should be ET. Okay, you make a correction, right? So this is what ET we have. So by writing all these equations, same as we have followed previous procedures in the normal incidents, we will get the boundary conditions. So internal we have this is also taken. So we will have this is the unit 7, right? So we go through this, right? So what we'll do is in the next class, we'll see in the next unit, that is unit 8. So if you have any doubts, you go through this. If you have any doubts, you can ask in the next class, okay?